Let's now have a look at evaluating the performance of our machine learning model. This is important so that we can make sure that those models really meet the desired objectives, and they will also perform then well later on when we want to use this model with some new data. So this process uses various metrics and techniques. They all are there to assess the accuracy and the overall effectiveness of our model. And in this lecture, we want to have a look at how this works. So first of all, we need an evaluation data set. So after we have trained the model, we need to evaluate the performance, and for this we need to use a distinct data set. So those data sets that we use in training and then testing, we typically partition them into 3 different sets. So the first one is the training data set. So this is used to train the model so that the model can learn the patterns of the data. Then we also have a validation data set. This is used to fine-tune and improve the model. So this helps in evaluating how the model performs on data that it hasn't seen before during the training. And then also it uses this feedback basically to see how the model should be adjusted before we then have our final testing. And this is then done with this final test set. So this is the test set that we call it, and this is then used to assess then the predictive quality after we have done those improvements, this hyperparameter tuning, now on this test set. So here again, this is data that the model hasn't seen in the training, so we can really see how this now is performing in terms of the accuracy, so that we can make sure that we really meet those performance standards before we deploy our model. All right, so these are our data sets. And now let's talk about a few important concepts. So understanding the model fit is very important to understand how we can diagnose issues with the accuracy of our model. And we can determine whether a model is overfitting either or underfitting the training data by looking at the prediction error on the training data and the evaluation data. So what does this mean, overfitting or underfitting? Let's first clarify this. So overfitting occurs when a model is performing very, very well on the training data. So even maybe a little bit too well, and then it is performing poorly on unseen data. So on our testing data or our validation data. This is indicating that it has learned basically the noise and all of the details specific to our training data set. So then it was just too close to the training data set. So it's exactly mirroring the training data. And then we have also underfitting. This occurs when a model is basically now too simple. So while overfitting was too detailed and too complex, now underfitting is too simple. So then it doesn't really capture all of the underlying patterns in the data, and then this also leads to a poor performance on both the training data and also the testing data set. And a model is considered balanced when it performs well on both the training data and also the evaluation data. So in here, bias and variance are 2 very important concepts that are affecting the model's performance. So let's quickly talk about them as well. Bias is the difference between the predicted value and the actual value. So this is basically the error. And a high bias is indicating that the model might be not good enough. So maybe it's too simplistic and it doesn't capture the underlying patterns. We also have variance. This is the spread of the predicted values among the various data sets. So how dispersed is it? And a high variance here suggests that the model is maybe too complex and too sensitive to the noise in the training data. So here the predicted values might be too dispersed. And an ideal model has both a low bias and a low variance. So like this, it can accurately capture the real true relationship and like this provide consistent and reliable predictions. Now that we have those concepts out of the way, let's talk about specific model evaluation metrics. Very important and also quite practical. So let's have a look at this in the next lecture. Now that we had a look at the concepts about model evaluation, let's now dive a little bit deeper into the specific and most important metrics that are used to evaluate the models. And how you evaluate a model, so which metric you are using, this depends on the kind of model that you are using. So what kind of a learning problem you are trying to solve. And in here we will look at the most two important ones. We will look into classification problems and then also regression problems. So let's start with a classification problems. For those types of problems, we have the most important metrics that are the first one, accuracy. So this is the proportion of correctly classified instances out of our total instances. So a classification problem essentially is choosing between different classes. For example, a binary classification problem could say, is this true or is this false? Is this a fraud or is this not a fraud? Of course, we can also have a multi-class classification problem. In this case, we would have multiple classes. But we always try to predict whether in which class this falls. So is it a fraud or is it not a fraud, for example? And here the accuracy is just like this, the correctly classified instances out of the total number of instances. For example, if we have 100 emails and your model correctly classifies 90 of them, so either they are spam or not spam, then our accuracy would be 90%. So 90% of the total classifications are correct. Then we have the precision. This is the proportion of correct positive predictions. So this measures how many of the predicted positives are actually positive. So in some cases, this might be also an important thing to look at. For example, if your model predicts that 10 emails are spam and 8 out of them are actually spam, then your precision is 80%. So here this precision just focuses on how many of the predicted positives, in this case the spams, were actually correct. And then we also have the recall. This is also sometimes called sensitivity, and this is the proportion of correct sets that are identified as positives. So this indicates how many of the actual positives were correctly identified. So for example, if we have 20 actual spam emails and your model correctly identifies 15 out of them as spam, then our recall is 75%, 15 out of 20. So recall is about capturing as many of the actual positive cases, in our case spam, as possible. Then we also have the F1 score. This is now the mean in some way of the recall and the precision. So here we are trying to find a balance between those two metrics. So if both of this is of course important, we can optimize this by looking at the F1 score. So if we want to have both of them as high as possible, we can see that this is what we can have a look at this by using the F1 score. So for example, if our model's precision is 80% and the recall is 70%, then the F1 score would be around 74-75%. So this is just balancing the precision and the recall in one single metric, and is important when we have to have a good balance between precision and recall. Then we also have the so-called area under the curve, or to be more precise in this case, the area under the receiver operating characteristic curve. Very complicated name. This is plotting essentially the true positive rate against the false positive rate. So this measures the model's ability to discriminate between the classes. And of course, we will have a look at this in practice. This helps us to understand this a bit better. But essentially, we need to define a threshold of when, with what confidence level we want to classify something as spam. So for example, if the model is 70% sure that this is spam, we want to say maybe this is enough confidence so that we say that this is a spam. So we classify it as spam. And here with those thresholds, we can set them in different ways. And if we use the A, and this curve is basically representing how well our model will perform across those various thresholds. So these are the classification problems. And now let's also have a look at regression problem metrics. So a regression problem is essentially where we try to predict a value. For example, we can say, we have an employee and we need to predict the cost of this employee, or like the salary of the employee. So this is not a class, but we need to predict a number, and we use some kind of regression for this, so some kind of a regression algorithm. And here we have the mean absolute error. This is now the average absolute difference between the predicted value and the actual value. So this is pretty straightforward to measure the error. Then we also have the mean squared error. This is now the average of the squared difference. So this would penalize larger errors more than the mean absolute error, because they will grow a bit faster. So here we have a little bit more emphasis on those larger errors, and they will be punished basically a bit more. Then we also have the root mean square error, which is quite similar than the mean square error, just that we take the root out of this as well before. And then lastly, we have r squared. This is now the proportion of variance in the target variable that can be explained by the model. So this is indicating how good is the fit of the model. So this is often used for how well our model fits. So essentially it's the variance in the target variable that is explained by the model. All right, so those were the most important metrics to evaluate the model performance. Now let's finally also recap a little bit about machine learning solutions, how they can be developed, and to better understand how this can be done, we first need to understand its core, which is the machine learning development lifecycle. So this lifecycle is basically an end-to-end process for developing, deploying, and also of course maintaining our machine learning models. So therefore, let's have a look at this life cycle in more detail. The first phase in this life cycle is identifying the business goal or the business problem. So in this initial phase where the business needs to now define the goal, this is where we need to define exactly what we want to achieve with our model and with using machine learning. So this includes what is the value that we are trying to get out of it? What are maybe the success criteria? And also, of course, what might be our budget? So those objectives, they will be defined by the stakeholders, and then they set the foundation for our entire machine learning project. After that, we have the second phase, which is the machine learning problem framing. So in this phase now, the business problem will be converted into a machine learning problem. Here, data scientists, data engineers, machine learning architects, and also subject matter experts, they all need to collaborate so that they can determine if actually machine learning is the right approach for this. Also here, they need to do a feasibility analysis so that they can ensure that the problem can actually effectively addressed using our machine learning approach here. And then after that, we have the third phase. In this phase, we have the data processing. So here, the data is transformed into an easily usable format. So here, the data processing involves, again, multiple steps. We have data collection, and we talk about this in more detail, of course, in a bit. So here, data collection, data pre-processing, and also feature engineering. So data collection is where we have the raw data that is gathered from various sources. Then the data pre-processing, where we now have this raw data available, and now we need to pre-process it. This means we clean it, we transform it, and essentially we prepare it for the model training. So this pre-processing also includes handling missing values. Maybe we need to clean some outliers. There are some errors. So all of this needs to be cleaned so it's prepared well for the model training. And then, of course, the next step that is also associated with the pre-processing. And then the next step that is also associated with this processing of the data is feature engineering. So this is now done to create additional features. Basically in here, we can, for example, have something like, let's say, we have our original data, which might be just the date, so 1st of January, for example, and we can build additional features out of our existing data. For example, when we have 1st of January, maybe this can be transformed also into a weekday. So we have Monday or Tuesday, or maybe the month, January. So this can be transformed and engineered out of our existing features, and this can make the model understand the situation better, and like this the model can work more effectively. So we can do the same thing also about other data. So this can all be engineered, put together. Maybe we can do some calculations, make some averaging, add some numbers together. So like this, we have additional features. This is why we call it feature engineering, so that we can basically enrich our data and get a better result with this. And then afterwards, we have the fourth phase, which is now the model development itself. So in here, we have now training, tuning, and also, of course, evaluating the model. And this is an iterative process. So oftentimes it requires multiple cycles of refinement. In the beginning, the model is of course now trained with this prepared data that we have done so far. And also here we have something that is called hyperparameter tuning. This is done to optimize the model performance. So hyperparameters are essentially part of a model. So depending on what type of model or what type of algorithms we are using, all of those algorithms, they have a set of hyperparameters that define how the algorithm works. For example, we have a decision tree. With this decision tree, we can set some limits. For example, how many nodes do we want to have, or what is the depth of this tree? So these are essentially all hyperparameters, and depending on the data that we have, some hyperparameters, so they are essentially giving us the frame of how the algorithm should work. So within these limits, this should operate. And in here, we can see that in some cases with some data, those hyperparameters work better, and with other cases, the other hyperparameters work better. So this is why we call it tuning. So we have hyperparameter tuning, and this is again an iterative process. We need to evaluate it, one set, and then we can maybe change it. So we can go through a set of different hyperparameters to see which ones perform the best to have our final model. And of course, these hyperparameters are called hyperparameters because they are not the actual parameters of the model. They are defined in the training. So depending on what the data looks like, we have in the training then exactly how the tree is split. If we, for example, stay within this decision tree algorithm, then we have exactly the splits, but they are just giving us the boundaries and defining how the algorithm works in itself. All right, so all of this is done, of course, to increase the performance. And of course, then once we have done this, we have also the development. Once we have done this, we also have the model deployment. So in here, we are now, once we are happy with how the model is deployed, we can now deploy it into production. So here we are now ready to generate predictions from it against new data that is coming, so that we can actually solve our business goal. And of course, this is a repetitive cycle, as we have said. And after the deployment, of course, we also need to monitor our model. So this is important because we need to ensure that the model maintains the level of performance that we have maybe defined, our requirements, because sometimes we have some issues, and of course we want to detect them as early as possible so that we can get the best possible benefit out of our model. And of course, this machine learning lifecycle is a repetitive lifecycle. This brings us to the last point of model retraining, because of course we get new data, so the situation in reality can change, and therefore also our maybe requirements might also change, and also the model needs to work in a different way if the data and the reality is changing. So therefore we need to do some retraining to adjust the model so that it remains as accurate and as relevant as possible. And now in the next lecture, now that we have this overview, we want to have a look at how we can use Amazon SageMaker. So how the services that are offered in here, they allow us to follow every step of this machine learning development lifecycle, and how this can be mapped against Amazon SageMaker, which is the biggest service about machine learning in AWS. So that's what we are doing in the next lecture. Now let's talk about a topic that sounds in the beginning a little bit more theoretical, but these are actually super important concepts, and also in regards to the exam, this is very important. So therefore, let's now talk about MLOps. This refers to the practice of operationalizing and streamlining our end-to-end machine learning lifecycle all the way from model development, deployment, up to monitoring and maintenance. So this helps to ensure that our models are not just developed, but they are also deployed, they are monitored, and of course then also retrained systematically and repeatedly. So this is basically an extension of the DevOps principles and all of those practices, but it is now specific to the domain of machine learning. So what are the goals of MLOps? A goal of MLOps is that we get our machine learning workloads into production and we keep them operating. And to meet this goal, MLOps adopts many, as we have said, DevOps principles and all of those practices for development, but also now training, deployment, monitoring, and the retraining of our models. The aim here is that we use MLOps to do the following things. So first of all, we want to promote a culture of collaboration between data scientists, data engineers, but also software engineers and IT operations. Additionally, we want to also, of course, increase the pace of the model development. This is always important. We can achieve this through automation, and we want to minimize, of course, like this, our deployment time. And of course, we also want to improve the quality metrics through testing and monitoring. And of course, also governance through providing transparency, explainability, auditability, and of course, security of our models. So for this, we use model governance. And now let's talk about the benefits of MLOps. First of all, we have productivity. So by providing self-service environments with access to some curated data sets, we can move faster. So we can enable the data scientists and the data engineers that they just waste less time by just missing some data or data is not valid. So they have access to curated data sets. Additionally, of course, it is more reliable. So we can incorporate CI/CD best practices. So like this, developers can deploy more quickly with a better quality and a higher consistency. Additionally, of course, we can automate all of the steps in our machine learning development lifecycle. And like this, we can ensure a repeatable process. And this includes how the model is trained, how it is evaluated, how it is versioned, and how it is deployed. Also, of course, by versioning all of the inputs and outputs, all the way from data science experiments up to the source data to the trained models, we can demonstrate exactly how the model was built and how it was deployed. So like this, it is more auditable. And of course, data and model quality. So with MLOps, we can also enforce some policies. They are there to guard against model bias, and we can also track changes so that we can see what are some of the statistical properties and how the maybe model quality changes over time. Now let's talk about some of the key principles that we can use so that we can actually achieve those benefits. So first of all, we have version control. This is very important for reproducibility. Here, our machine learning workflows must track changes to different assets like the data, the code, and the model. So like this, it can be rolled back to previous versions when it is needed. Also, automation is important. So for repeatability and consistency, and also of course scalability, we can automate the different stages of our machine learning pipeline, which can include something like data ingestion or data pre-processing, but also of course model training, validation, and also the deployment of our models. And also, of course, we can automate testing, which helps to just discover the problems earlier and fix the errors faster. And of course, CI/CD, which stands for continuous integration and continuous delivery or continuous deployment. So here we can also just continuously test and deploy our assets. And like this, we can also, for example, automatically deploy newly trained models or our predictive services. Additionally, also model governance is something that is basically a structured process for reviewing, validating, and approving our models before we deploy them, so that we have some checks, for example, for fairness, bias, and ethics. And governance essentially manages all of those aspects of our system so that it runs efficiently. Now let's have a look at the AWS services that are relevant for MLOps. Here, first of all, we have SageMaker Data Wrangler for preparing our data. So this is basically a low-code or no-code tool that is providing an end-to-end solution to import data, prepare it, transform it. We can engineer the features and analyze the data all in a web interface. So this makes it very easy to do this data preparation, data pre-processing and importing of the data. We also have the feature store. So the SageMaker feature store just helps all of the people that work in our projects, be it data scientists, machine learning engineers, so that they can create, share, and manage the different features of the machine learning development. So for example, we want to train our model, we want to enrich it with additional features, for example, some weather data, or some other kind of general data, maybe some holidays. This can be all stored as features in the feature store, and then it can be reused. It can be shared, and we can modify and manage those features that are necessary for the development of our machine learning models. Additionally, also SageMaker provides different types of training job features. So we have here, for example, some built-in algorithms that we can use, or we can also create our own custom algorithms. And we have these SageMaker experiments. They help you to experiment with multiple combinations of data, different types of algorithms, different configurations of our hyperparameters. So here we can, like this, test all of this, experiment with it, and then observe what is the impact of those incremental changes on the model accuracy. So we can track it, we can see it if we experiment with it, and then step by step see what is the best combination of algorithms, parameters, so that we can get the best performance of our model with the best configuration. Additionally, we also have the SageMaker model registry, where we can catalog our models, we can manage the different versions of the models and manage the approval status also of a model, or deploy models into production. For this, we can use model registry. And also with SageMaker, we can deploy our machine learning models so that we can make the predictions with them. This is what we call inference. So here we have a broad range of machine learning infrastructure and model deployment options available so that we can meet our inference needs. And also we have model monitoring. Here we can monitor the quality of a SageMaker model in production. And finally, we also have pipelines. Here we can use the SageMaker model building pipelines so that we can create an end-to-end workflow that is managing and deploying the SageMaker jobs. So this is it. And of course, this was just an overview. Actually, we don't need to dive here into all of this depth. This is not necessary for the exam at all, but we got an overview over the machine learning operations. Hope it was helpful, and see you in the next lecture.